A, right? We can draw a free body diagram down from the bottom. So acting up at A, we have AY. Internal to this, we have the internal force in section AB, okay? And that's going to equal minus AY, right? It's in compression. And so from that, I can write this elongation, right? This elongation here is going to be the internal force times the length over the cross-sectional area times Young's modulus, right? So it's going to be NAB times the cross-sectional area of AB. Oops, that's AB. Over the length of AB, right? Young's modulus of AB, right? Likewise, for this section, if we were to draw the free body diagram from, here, we'll do it from the top. So this is now C, and I have the force acting up here is CY. And balancing that is my internal force in section CB. In this case, it's clearly going to equal to CY. So that internal force in CB times the cross-sectional area of CB. I'm sorry, I'm doing this backwards. I'm so sorry. It's force length over area. These are lengths, these are the areas. Okay, it doesn't really matter though. Yeah. Right, that all has to equal 0. That's my second equation. That is my compatibility equation due to the second constraint. All right. Well, in this case, we know the cross-sectional areas are the same and Young's modulus are the same. So I can just multiply through by those, right? They're just going to cancel out, correct? So it doesn't really matter, right? Multiply by the cross-sectional area and Young's modulus. It's the same for both segments, so it cancels out. Multiply by 0 on the right-hand side, they go away, right? NAB, we said that is we already figured that out. That is minus AY from this free body diagram. From the second free body diagram, we figured out the internal force in section CB is CY. We know the length of AB is 2 meters and the length of CB is 1 meter, okay? So that now gives me this compatibility condition is as follows. 2 meters, or I should say minus 2 meters times AY plus 1 meter times CY equals 0. I can divide through by meters, but basically you can get that. CY equals 2 times AY. Okay, that's still 2 unknowns, but now I've got a second equation. So I've got this equation 2 that comes from the compatibility condition. And we also had our equation of equilibrium. Right, that was my first equation. That's from the equation of equilibrium. So now I have 2 equations for 2 unknowns, and you can solve this, right? So in this particular case, you can see, well, there's a couple ways you can do this. You can substitute in for CY, 2AY, and then you get that 3AY equals 3 kilonewtons. So AY equals 1 kilonewton. And then you can take that and put it back into the original equation, and then you'll see that CY equals 2 kilonewtons. All right. And so it's solvable. Okay. So now we've solved it. Okay. It's a unique solution, obviously. Like you can't have physical problems where there's infinite number of solutions. It only works in quantum mechanics, right? Not in deterministic mechanics. And we have more, the problem is over constrained. but that's fine. Every time you have an extra constraint, there's an additional compatibility condition. In this case, it was that the total elongation is 0. And then you can take that compatibility condition, recast it in terms of your unknown variables, those support forces, and then just solve for that situation. So we could have even had an additional third constraint that would have introduced a third unknown. Then we would have one equation of equilibrium and then 2 compatibility conditions. And we'll be able to solve those 3 equations, okay? All right. Is there any questions on that? Now, obviously, once you know the forces, I can go back and figure out the stresses and everything. I can figure out how much AB compresses and how much BC elongates or whatever else the problem wants you to find out, right? But that's the approach, okay? You have to always supplement the equations of equilibrium with a compatibility condition. It's a displacement condition. Each redundant constraint will have its own compatibility condition, right? Like, for example, you know, I won't solve it, but I'll just draw it, right? Let's say we had something that looks like the following. I'm going to put, fix it here. And we'll fix it here. And then we're going to put a plate on here, right? And we can even fix this plate, right? And then you can have a force in here and a force in here, right? So here we have, it's still one-dimensional, so we only have one equation of equilibrium, sum of forces in the y direction, but we're going to have 3 unknowns, right? Those are 3 reaction force unknowns. So I got 3 unknowns, 1 equation. So we can do 2 compatibility conditions. Let's call this A, B, and C again. So we know that we need 2 more compatibility conditions. We know that the elongation of AB has to equal 0 because this is fixed and this is fixed. And also we know the elongation of BC has to equal 0. Okay? So I added this second extra constraint, and that gave me a second compatibility condition, right? And so you would do the same thing, right? You would have 3 unknowns, 2 compatibility conditions, and 1 equation of equilibrium, all right? And that's the way we'll do these, okay? All right. All right, so now let's have you all do a problem, okay? Let's look at the following problem. So this is almost, it's the same problem, okay? It rotated onto its side, okay? Even the letters are the same, all right? The letters are the same. But what's a little bit different here is oh wait, I don't want to do this one. Let's not do this one. Let me find. I don't want to do this one yet. This one has a friend where it's rigid, right? I don't want to do that to you yet. Oh yeah. Okay. So let's not do that. Let's do. I don't know why that came out that way. It's so weird. All right. I don't know. Okay. Let's. I don't know why I did that. All right. Let's try this again. All right, so I just cut and paste the 2 problems in here, but let's just do one of these, okay? Let's look at, for now, let's just look at, let's ignore this one, okay? All right, so in this particular case, it's, like I said, it's the same problems we had before, except the area is not the same, right? We have a different area in AB than we do in BC, okay. Actually, even the length ratios are the same. And well, it wants you to find the support reactions at A and at C in terms of P. Okay, so P, even though it doesn't give you a number value, we can assume that P, A, and D are given. All right. So what they want you to do is find the reaction forces AX and CX in terms of P, A, and E. And they give you the, and also Young's modulus is given, right? E. All right. Okay. The approach is still going to be the same. You're going to have an equation of equilibrium, AX plus P plus CX equals 0, but you're also going to have the compatibility condition that the elongation of point A relative to C equals 0. Okay? All right, so I'm going to break you up into groups, and let's see if you guys can work that through. So everybody do their own work, but try to work in groups again, okay? I will not have you submit this one, but I'll have you submit the next one, all right? If I can break you up in groups. All right, okay, here you go. Have fun.
Someone raise your hand. Please. Andrew, go ahead.
Hi, first, thank you very much for the presentation. Yeah. Those topics are very interesting. I was wondering, I can see in most of the applications you're always trying to find a closed form solution. And for that purpose, you have to linearize the system at some point. What is the main inconvenience that you can identify in doing so, and why do you prefer to do that instead of working the system as non-linear?
Well, non-linear system is, well, actually, I would say not exactly I was linearize the system because I just decompose them into subproblems to some linear problems. But in a whole, I'm still solving the original nonlinear problem. As long as the subproblem, the whole pipeline converges, it will recover exactly to the original nonlinear problem. For example, the first part, QCQP. And for the reason why I was doing so, because there are a lot of advantage of solving convex optimization and linear system. You can get some good guarantee. Say, if I solve this subproblem, if it's convex, I can guarantee I solve it globally within reasonable or polynomial time. But if you solve nonlinear directly, it's hard to say how good I will solve this problem too, and it's ambiguous where I will get. It will depend a lot of issues. Yeah.
All right, thank you.
Yeah, thank you for the question.
Any other questions or comments? Yeah, I have one. I have a little more of a comment. So I guess Christy told a lot of these things you just mentioned is way above with my knowledge levels. I have not many questions to ask you there, but I did see one maybe potential collaboration stuff we can do. So you said you want to use machine learning and AI for manufacturing or for additive manufacturing, right? So Can you elaborate on that a little? Like, how do you see application of machine learning on manufacturing of materials?
Yeah, well, I do have already seen, I have colleagues here working on machine learning and fluid mechanics. Like, if, for example, if your dynamics is too hard to use exclusive repressions of the differential model, then we can use samples and use deep learning technique to learn such a model, which can be quite accurate. And for materials, I think I was curious. When I was undergraduate, actually, we to design component material, which is based on topology optimization. But if in manufacturing of material, there are still a similar decision process like that. So if we, in a decision process, if you have decision to make, then we can use reinforced learning or deep reinforced learning to parameterize all of the decisions you need to make and all the inputs like what we know in the manufacturing material as the input of the network and this properly defined goal or reward function in the reinforcement learning sense that we can design the variable you want to have in this deep learning technique by optimization by optimize the neural nets. Which the output, what kind of design variable you might have.
Mhm. Yeah, that's great. Yeah, especially on the composite side discussed. And right now we're doing some hypertrophic composite for the obviously the ability of these composites to be used. So we can find a way to having I guess different application scenario like great. So thank you. Good time.
Good. Can you hear me?
Yeah, I could.
Okay. Hello. Thank you very much. I'm sorry I didn't join at the beginning due to my classes.
That's okay.
I'd like to ask you one very simple question. And here, and you have to go on to such applications for the video code. Very, very considerable. What is that? What is that code? How do you explain a very important way of simple way that students can understand?
Basically, it's all about how the using lab math yeah, if you want to something like that's my to all the entities. But if you ask in general, I think if you ask one person, people are really trying to explain them without mathematics, with this English language, like everybody is not really getting it right. And study to explain it to a video before beginning to the questions.
Thank you. Thank you very much.
Mm.
Thank you. Maybe one last question. One last one. Very good.
There's some.
Yeah, I think Luis, um, I think that Sierra, it's more difficult than scale to one R. So I just was wondering why what's the benefit of the skill set and the numbers or why don't you just stay with the same parameters you have?
Scaling up the story point, the more using iron.
Yeah.
Okay. Yeah, you are, you have a big, for example, warehouse, you have, you can get levels, you want them to collect, calling this, where you calling this, so that they can see the common control, and you will have this many entities, you know, so that's important, because on that person, I'm using because I'm using the application, and that's the application coming together, so I'm using working for like structures. Thank you.
There's one more thing here, that section with network translation, you need to select models that for transfer learning.
Yeah. Uh, oh, first problem is, for example, this problem, if you want, you see the real talk, is depend on that. There's a we can apply policy study that on different scenarios to you. For example, we can test for the different number of things in this scenario because our is in function style is interesting to remember because like if you do message that you get from all the others, but if you do something, for example, something simply something from the members and then of course this is something more complicated. But in the end, in this case, it should be very comfortable. Yeah.
Wrapping up now, 3 minutes over time, that is possible. Next, is the collateral.
All right, looks like everyone's back, I think. All right, so I'll kind of go through this quickly, but if there are any questions that you have, please feel free to you can chime in now or after we get done with it, okay? So, all right, so here's the problem again, as written. So we want to find AX and CX, and we have sum of forces in the X direction. So on this full, on the total free body diagram, right? We have AX plus CY plus P equals 0. All the forces as drawn are going to the right, so they all sum up to 0. Okay, so obviously one of them is going in the opposite direction. All right, or both of them are going in the opposite direction. Okay, two unknowns, right? One equation. So we're going to use the additional compatibility equation that the total elongation from point A relative to point C has to equal to 0. So again, we're going to break this up into the elongation of section AB plus the elongation of section AC. Those two added together equal the total elongation, which has to go to 0. So that's what we got here, right? So the total elongation, delta AC, which equals to the elongation of the two segments where everything's constant, has to go to 0, all right? So now we have to get those elongations in terms of the unknowns, right? So, the elongations for each segment, it's the internal force times the length over the cross-sectional area times Young's modulus, right? So each one of these sections, the internal force is going to be related through to the unknown supports. So if we look at a free body diagram where we cut through between A and B and look at the left side, we get the following, and that exposes the internal force in AB, and we can see that it's equal to negative AX. And likewise, we can look at a cut on the right-hand side between B and C. Here's that free body diagram. And you can see that the internal force in section BC equals the support force CX. Right? So now we know N in the first section is minus AX, and N, the internal force in the second section, is positive CX. All right. So we put that into here, right? So that's all we're doing, right? So this first term is the elongation of section AB. It's the force in it, which is minus AX. Its length is 2A. Its cross-sectional area is pi over 4 times the diameter squared. So there's the diameter, it's D. And then Young's modulus is E. For the second section, or segment, I should say, the elongation of that is its force, which is CX is the force inside of it. Its length is just A. And its cross-sectional area is 4 pi times its diameter squared, but its diameter is 3/4 D, so I put that in there, right? And the the Young's modulus is E. So you can see A's cancel out, as well as the E's, as well as the D squared, right? I get rid of the D squared, right? And that gives me, well, let's 2AX times pi. Well, actually, the pi over 4 is canceled out too, right? Get rid of those. So get rid of the pi over 4, move it a little easier. So now I'm gonna 2AX. Well, okay, let's do an extra step. I won't do it. CX over 3/4 squared equals 0. That's what's left, right, after we cancel everything out, right? Or in other words, CX equals 3/4 squared, right? Times 2AX, which equals, that's 9 over 16. So that's 9 over 8. 8x, if I did that correctly. Did I get that right? 9 over 8. Yeah. 16. Right. All right. So now, right, here's our second equation, or I'll call it equation 3, but now we can solve 1 and 3 for AX and CY, okay? All right, before I solve it, are there any questions up to that point? Be careful about the sign, right? That one's in compression, right? Make sure you have, because we have to make sure we keep that negative in there. Otherwise, it's, it's going to screw up the calculation, right? But that one is going to be in compression, right? Most likely, right?
Professor, why is 3/4 squared if we cancel the d square in the other side?
Oh, well, we just canceled d squared, not 3/4, right?
Okay.
You see what I mean, right?
Yeah.
This one, the diameter of this one is equal to 3/4 d. This one, the diameter here is just equal to d, right?
Okay, yeah.
So the pi over 4 d squared cancels out, but underneath the cx term, you still have the 3/4, right? See, they're different areas. It's just that they're using it in terms of that, variable d, right?
Okay.
All right. Okay,
Thank you.
sure. And okay, so, well, there we go. So I can take, knowing this, I can take that and put it right into equation 1. So I get 11/8 AX equals negative P, right? Or in other words, AX equals negative 9 over 11 times P. All right, so it's going the other direction. I can take that and put it into here and get CX, and that's going to give me CX equals 9/8 AX Did I do this? Did I make a mistake on this one? 11/8. I'm sorry. This is an 8th. Right? Because 9/8, what am I doing? 9/8 go into, what was the other equation? Right. I mean, I didn't write, but we got AX plus CX equals minus P, right? So if I put in for CX 9/8 AX, this is 8/8. I'm sorry, I screwed that up, right? I'm going too fast, right? So I get 8/8 plus 9/8 is 17/8, right? This is 17/8. Okay, and then that's going to give me here minus 8/17. All right. And now if we take that and again put it into here, we get that CX is 9/8 times AX, but AX is minus 8/17 P, so the 8's cancel out, and we get minus 9/17 P. All right, so that's what's going to look like, right? So if we redraw it, right, here in this direction, we have the force P acting, and then at C, it's actually in the opposite direction that we drew, and it's 9/17 P. And likewise at A, it's also in the opposite direction, and that is 8/17 P. And you can always do a couple of checks. So first of all, you can always go back and make sure that it still satisfies equilibrium, so you didn't make any algebra errors. And here you can see if we add 8/17 and 9/17 together, it's 17/17, and so that works out, right? It's a check, okay? Fair enough? Or are there any questions on that one? All good? Okay. All right, well, let's keep going then. Let's look at another one. Let's see if I can do the cut and paste. Let's just clear this. All right, so here we're going to look at problem 431. All right, so I cut and paste. It's again 2 problems related to the same figure, but let's not do this one. Although you could, it's not that hard. So let's look at 431. All right. So this is pretty typical, right? So we have reinforced concrete column here, right? So the column has this concrete core, which has a diameter of 8 inches, right? 8-inch diameter of the concrete. But inside of it are 8 steel reinforcing rods, rebars, right? Each one of them has a diameter of 1 inch, okay? All right. What it wants, and then there's a total force applied on top of 200,000 pounds, okay? And it wants you to figure out the normal stress in the concrete and in each steel rod, all right? All right. So again, well, you probably can guess this is a statically indeterminate problem, but it's a little bit different than we've looked at before. If we were to draw the free body diagram of this top plate, we would have the following. All right, there's the top plate. So acting down on the top plate is the 200 kip force. Now, what balances that? You have a force from the concrete, all right? And you also have a force from the steel rods. So there's 2 ways we can deal with this. It really doesn't matter. I can treat all 8 steel rods as one piece, or I could think of it as 8 individual steel rods, okay? I'm going to just, it doesn't matter. You can do it, but let's just have one force for the steel. This is the force from all 8 reinforcement bars. Okay? All right. You could consider FS as from 1/8 rebar, and then you have to multiply that by 8. It doesn't, but you get the same answer, okay? But we'll consider FS to be the force in the steel from all 8 reinforcement bars added together, right? All right, so here we can do sum of forces in the y direction, and we can get FC plus FS equals 200 kips, right? Okay. So one equation, two unknowns, right? So we have the same situation here, all right? So I need to have a compatibility equation. Anybody got an idea of what compatibility condition could be conveyed here? So obviously the total elongation is not zero, right? This will compress. I think that's pretty a reasonable assumption. I think we all are down with, right? So it's not like I can say the elongation is zero, but there is a compatibility condition that's here. All right, well, let's think of it this way. I'm going to call delta C. That's the compression of the concrete. And then delta S is the compression of the steel rods, okay? Is there a relationship between those two?
Aren't they equal?
Right, they're equal. That's right. So it's a little different form, and that's because the other problems, what we saw were the elements were in series. In this particular case, the elements are in parallel. Does that make sense? So you can think of it as like the concrete and then the steel as being elements in parallel. And in those cases, you know, we don't know what the displacement is, but we know they have to be the same. The concrete and the steel have to displace by the same amount. So fine. So here is our second compatibility condition, okay? So again, you know, you can figure out the elongation of the concrete is going to be the force in the concrete times the length of the concrete over the cross-sectional area of the concrete times Young's modulus of the concrete. And likewise, the force in the steel, the displacement of the steel is the force in the steel, the length of the steel, cross-sectional area of the steel, Young's modulus of the steel. Now the lengths are going to be the same, so they'll cancel out, but A and C are different, okay? So in this particular problem, let's say that E for steel is 207 gigapascals, okay? And then the E for the concrete is, where did I say? 4. Oh, wait, I'm sorry. We're in, not metric, we're in imperial units. So let's fix that. Okay, let's not do that. What is going on here? Oh, I hate when it does this. Okay, finally, there we go. Delete this. Okay, so the E of the steel is 30 times 10 to the 6th psi, and then the E for concrete is 4 MSI, right? Right. All right. So put you in groups, figure out FC, FS, and then from that, you can get the stress in the concrete and the stress in the steel, which are just going to be those forces over the areas. They're going to be compressive, okay? So I'm going to put you back into groups, the same groups. But in this case, I want you to do as last time, work in the group. It's fine if your work looks the same, that's fine. But I need you each to individually submit to Gradescope on this one, okay? Was there any questions before I send you back into your rooms? Without dinner? Okay.
Professor, you muted, I think.
You're muted, sir.
Well, it doesn't matter. I'm not, probably not that important what I gotta say anyway, right? So, but yeah, so I forgot what I was saying. So submit your stuff into Gradescope, right? Whatever you have. If you, like, again, I'm not grading you on your correctness. I just want to see, you know, how we're doing in solving these problems, right? It's good to get a little feedback on how we're doing these things before I grade the exams. Okay. So that's the point. So please, you know, post what you have. All right. I'll post the solution for this problem as well. Okay. It's actually one of the homework problems anyway. There are a couple other ones that are, so pretty much you either have the elements in parallel or in series, but there are also other ones that look a little bit like this. I don't know. Am I still sharing my screen? I don't know if I am or not. Okay, let me share my screen.
No.
Now I'm sharing the screen.
Yes, sir.
Okay. So there'll be some other ones where it's like, okay, here's a wall, right? And almost like what we did before, but there'll be a gap. All right. And so, like, let's say there's a force P here, right? And this is, let's call this point A, B, and C. But there's a gap here of like 0.02 inches. All right. Well, in that particular case, you know, assuming the force is enough to get the bar to close that gap, which it will, otherwise the problem would be in the chapter, right? You know, the compatibility condition is not going to be that the elongation from A relative to C is 0, but it's going to be that that has to equal the gap. Does that make sense? So the ones like that, like there's another one where you have like the crane with 2 wires holding up a weight. And one wire is like 0.06 inches longer than the other one. All right. And in that case, like if this is wire 1 and this is wire 2, right? It's not going to be that the elongation of wire 1 equals the elongation of wire 2. If wire 2 is longer, that means wire 1 has to stretch by that amount before it starts to even pick up in wire 2. Does that make sense? So you would have 0.06 plus. Does that make sense? I mean, if you think about it, I think it does, right? If wire 2 is longer, when I first put the force on here, it's just wire 1 that's going to see the force until it stretches by 0.06, right? Then once it stretches 0.06, now the 2 wires are the same length and they'll continue to stretch, right? So that's the elongation has to be the same for both. The elongation of wire 2 equals the elongation of wire 1 plus the amount it has to stretch before they become the same length. Okay? So they're kind of the same, but a little bit of a twist on it. So you'll see ones like that. And then other than that, they're all the same. Okay? I'm going to put there's also videos for assumed force. They show you to do assumed force. Look at those. I forget which problem we solve by assumed force, but I do a problem both by this method and then assumed force. Assumed force is a nice way to do it. Maybe I'll cover it real quick on Tuesday's class, but as long as you can do it one of the 2 ways is fine. All right. All right. Any questions before I cut you all free? Okay. Have a good weekend.